very special thing on our Multiblade application. You already are looking at my screen, and I have this very nice part for machining of an impeller. So today what I'm going to do is we're going to see this particular part being cut on SolidCAM's Multiblade application. The Multiblade application basically is a very special application meant for cutting impellers. You can cut impellers with splitters, without splitters, with a single splitter, with a double splitter. It doesn't matter what kind of a part you're throwing in at the application. It will do the part as long as it's an impeller. So it's a very specific module meant for cutting impellers. Straightforward module, not much of clutter in terms of parameters and in terms of things asked to machine. No geometrical constructions needed because it can do machining straight away on the part. In many of the times that we're cutting an impeller or we're doing a 5-axis, the fillet plays a very crucial role because it can really make the programming of 5-axis parts very, very tough when you have a fillet at the bottom. Now, in the Multiblade application, we even handle fillets. We handle fillets which are constant in nature. We also handle fillets that are variable, like, for example, this particular fillet that we have. It's basically a variable fillet that we have. Okay, so we're going to start this webinar. Now, if you look at the stock is part of my history out here. It's basically a surface that has been a curve that has been revolved to generate a surface of revolution. Now, what I can also do is I can take a stock that's been turned in my other file. Basically, let's assume that I have two machines. I don't have a Milton machine, but I have two machines. One is a lathe, a CNC lathe, and the other one is a 5-axis milling. So what I've done basically is I've taken the raw stock, turned it on my CNC machine, and that stock is going to become my starting point for my 5-axis. Now that can be done. It's very easy. I'll go to my stock, define it. Now instead of 3D model, I'll select STL. Now, how did we create this STL? In SolidCAM, once you are into the Solid Verify simulation, when you run the simulation, at the end, when you finish the simulation, you do get an option to save this finished stock as an STL file. So you can just click on that and create an STL file out of that. So what I can also do is I can go there and pick up this turned stock. This is basically an STL file. So if you want to see how that file looks like, we do have the file. So I'm going to open that file. I have an STL viewer with me. So this is how my file looks like. This is the turned part which I've saved from Solid Verify. And this particular part, I would like to take it as my initial stock for 5-axis. It's pretty simple. Okay. So pick that, open. Okay, accept it. Right, so if I now look at the stock on the model, this is how my stock would look like. I've brought in that STL file, and that STL file is now going to be my initial stock. So I don't need to make create another model or anything. You could also do that, but you could also use this route. You could have a turned component, save that in Solid Verify as an STL file, and bring it in this file as my initial stock. All right. We have the stock. We also have our target, which is the part today, the impeller part, and we're going to start. Now, to make things much more easier, what I've done is I've created templates. Very easy to take these templates and apply it onto a different part. So I have created templates for a completely different part, from a completely different part, and that templates I'm going to apply here on this particular part out here. Okay, right. So I'll right-click on the operations, and I'll add an operation from template. So I've got a lot of templates out here. So I'm going to pick the impeller rough template that I had created, and I'm going to use the operation names as the template name itself. So I'll apply. Okay, that's my coordinate system and my submachine, because I'm using a 5-axis, so it has two submachines, 3-axis and 5-axis. I'm going to use the 3-axis submachine. Okay, right. So here we are with the template. Now, all I need to now do is to define what are my geometry. Now, a little bit about the Multiblade machining module itself. The Multiblade machining module basically comprises of 4 operations: roughing, finishing of the blades, that's the main and the splitter, finishing of the hub, and if you want to further finish up only the fillets, you can finish the fillets. Otherwise, if it's a constant fillet, and if you think that you're using the tool with a radius that is equal to the radius of the fillet, you can actually finish it during the blade finishing itself. So you have 4 operations, and these 4 operations form part of our multi-blade machining module. Right, we're going to start with roughing. Geometry. We have the strategy first here. We have 3 strategies: offset from hub, offset from shroud, and offset between hub and shroud. The offset between hub and shroud is the most commonly used strategy because it looks nice. However, there is an inherent issue when you want to use the offset between hub and shroud, and because especially for this impeller here. If you look at this size of this impeller, the width here of this blade and the width here are 2 different widths. When I put my depth of cut as 1 millimeter, that's the maximum depth of cut, that 1 millimeter depth of cut is put over this surface up here. So if it's going to put 1 millimeter here, naturally when it comes down, it's going to be much lower than 1 millimeter. So what looks like 1 millimeter here could look about 0.3 or 0.4. So it's basically giving you a variable depth of cut. Not so nice when you're talking about giving constant load on the tool. That's the reason I have chosen the strategy offset from hub. Doesn't look very nice, but it gives you excellent results because it will go from the hub 1 millimeter, so it will give you a constant depth of cut of 1 millimeter or 2 millimeter, whatever you've chosen, along the entire blade. So the area keeps varying, and the cut also keeps varying. So I already have the geometry with me, so let me pick from the long list of geometries. I'll pick face. Okay, so these are my blades, splitters, and fillets. So I've picked the main blade, the splitter, and also the fillets of the main blade. So what I need to do is I need to pick a group of blade which consists of 2 main blades and 1 splitter, so it understands where is the area to be roughed. All right, so this is my first geometry, and I would like to keep about 0.35 millimeter for my finishing, just very small amount of material. Hub, also I'm going to pick from here. Now the interesting thing here is you don't have to pick the hub completely. You just have to pick a piece of that hub. What SolidCAM will do is it will take this piece of a hub, it will generate a sketch of the particular surface of revolution and create a new surface of revolution that will define it as a hub. So only a piece of surface is more than enough. You don't need to pick everything that's there underneath as hub. All right, so let's pick this as my hub. Let's go to a tool. And the tool today is a 12 taper ball nose. It's a 12 diameter, a taper ball nose, and we have got the tip diameter as 5 millimeter with a tip radius of 2.5. So it's a ball nose, taper ball nose with a taper of 5 degrees. So we're going to use a taper ball nose now today for our roughing. Levels. Basically, this is the clearance levels and the style of clearance. So the style of clearance we are going to use is to the spear. And we use the auto detect position and dimension because we would like the software to take care of this. I don't want to define the spear radius and where is the position of the spear. I want the software to take care of this. So that's the reason I've used the auto detect position and dimension. We are simplifying it completely. Toolpath parameters. Basically, the first thing is the cut tolerance. So cut tolerance by default is set at 0.01, which you can leave it as it is, or you could modify it using the slider out here. Now the slider moves between 0.1 to 2 microns. So if you want anything more than 0.1, you could select the cut tolerance option and enter the tolerance that you would like to use. All right, I'm going to use about 0.1. In the technology, I need to define how many layers I want. Now the layers can be defined using either the depth of cut or how many number of cuts you want in that particular area. So I'm using a maximum distance, that is a maximum depth of cut of 2 millimeters, and I'm not going to use the side step here, but I'm going to say maximum number of passes, which is going to be 12. I'm going to have 12 passes in between the blades. Now, when it starts, you will notice that the 12 passes will be put between the main, this blade and this blade. But as it starts getting this area here, or as it starts getting the splitter, you will start noticing that the 12 passes will be put in between this two blades and these two blades. So the 12 is slightly a confusing kind of a number, but I'm explaining to you it's between this blade and this blade till it hits the splitter, and then between this blade and this blade, and then this side of the blade and this side of the blade. So 12 passes here, 12 passes here. Right. Tool axis control. Majority of the times in 5-axis, the tool axis control is the one that's the most trickiest thing, which takes a lot of effort to understand how are you going to position your tool in this particular part. You can either position it using the curves, you can either position it using the lines. A lot of options are available in tool axis control. Now this only complicates the programming. What you can do here is, in multi-blade machining, what we have done basically is we have cut off all those things, and we have kept some simple default values which generally work 99% of the time. And 1% of the time you probably have to tweak maybe the side tilt and the maximum lead angle. Otherwise, it's good for 99% of the parts. You don't need to tweak any of these parameters. So I'm going to leave these parameters as they are. I will not touch it. Link, you can see it's automatic. There's nothing that you can do unless and until you unselect the automatic, then it gives you options. But in automatic, it uses its own logic of linking between layers and linking between the slices. Okay, we do have a gouge check option, and this is to be used only when we detect a gouge onto an area that's beyond these group of blades. So if it's gouging on, let's say there is a surface up here, somewhere here, and if you feel it's gouging, then you could keep this surface as a check surface. But in this case, we are most unlikely to need it. Okay, roughing. Now, since this is going to be a single machining, and there are multiple blades here, you can use the rotation function, and you can put how many number of segments you would like to machine, and you can also determine which segments to machine. For example, you can say I have got 5 segments here, and I would like to machine only 3 of them and not all 5. And the start angle, you can start with all segments, and you can say my start angle is 90, or 5 divided by 360. How much would that be? Let's check. 72. So I can put my first start angle at 72, and the remaining will be the remaining 3 will be from 72, 144, and so on. Or you could say user defined. You can put which angles you need in this. But here I'm going to use only one of them. I'm not going to rotate it for all the other segments. All right, so I'm going to save this, and what we're going to do is we'll use the nice functionality of SolidCAM to calculate it in parallel, because it's going to take about 2 minutes, and in the time I'm going to start defining the operations for the next operation. That's the finishing of the blade. So I'm going to click OK. So we have our operation that's running. The best part in parallel, it's going in the background, and I'm free to put any other operation in this. Okay, so what I'm going to do is I'm going to right click on this operation, again add operation from the template, and I'll apply the finishing operation. Okay. I also have the template for finishing, so I'm going to apply the finishing operation. Okay. Now all we need to do now is to define the geometry. The geometry here I'm going to use is, the geometry that I'm going to use here is slightly different, because I'm going to use offset between hub and shroud. I'm going to use this strategy, although it doesn't look very nice, but rather it doesn't cut very nice. It looks very nice appearance-wise, you could say. So we have first the blades. So I think the blade's this, yes. This is the blade, faces 6. And we have hub, which is basically faces 1, that's the hub. And the shroud basically is, I think, this one, yeah. So even in case of shroud, I don't have to select all of them. I can just select one piece of shroud. It could be here or it could be on any other blade. So you don't need to select exactly the shroud on the same blade where you would like to do the machining. It's not necessary. You just need to select one shroud, one piece of shroud on the entire part. Okay. The tool that I'm going to use is, again, the same taper ball nose, the one that was used for roughing. Levels, toolpath parameters, technology. I'm going to use a maximum distance of 2 millimeters. We can cut this down. We can make it 1 millimeter 0.5, but it's for our purpose of understanding of the solution, this is not needed. You just make it at 2 millimeters, or you can just even put it at 1 millimeter. I mean, there's not much of a difference between putting it at 1 millimeter or putting it at 2 millimeter. The only difference here is that you will see a denser toolpath. So I'm going to use 2 millimeters. We're starting at 2% and we are ending at 95%. So we are not machining the entire width of the blade. We are leaving probably the lower part more, because we will be anyway using the fillet finishing to finish it. In sorting, I'm going to go spiral, starting from the leading edge. Now, there are some terminologies that I would like to explain. We have leading edge, and then we have the trailing edge. So the leading edge is the edge on the bigger side, or the bigger width of the blade, and the trailing edge is on the smaller side, the other side. So there's a terminology. So we are asking the tool to start from the leading edge. So it will start from here and then start spiraling around the blade. All right. Tool axis control. Everything is, again, like I said, default, because it works 99% on most of the blades. Link is again automatic, no gouge check. It's not needed. And we are not rotating the part, so I'm just going to save this. right click on this and I'll put this calculation in parallel, and in the meanwhile you can see that my first roughing operation has already been completed. Let's look at it. Nice. So very nice operation, and while the other operation is being calculated, I can always simulate the first operation. Let's go to the Solid Verify and run the simulation. Let me switch off the holder so it's more clear. You can see that the passes are now being put. The 12 passes are between the two main blades, the big blades. And once the splitter geometry is taken into account, as it goes more in depth-wise, the splitter geometry comes into picture. You can see that now it's starting to put those 12 passes in between the main blade and the splitter. So you'll see the passes are now much more denser than they were before. Okay, just going to pause it so you can have a look at the result. It's not complete, but it's starting on, so let me run that simulation further. If I actually also show you a much more interesting simulation on the machine, you'll like it. So I'm going to stop this and I'm going to go into the machine simulation. The machine today that we're using is a DMG 60 EVO evolution type machine with a Heidenhain ITNC 530. So this is the machine. Let me switch on the entire machine. CME 80 EVO, sorry, it's not 60, but it is 80. So we have this is as our machine. And let me open the door. Okay, and let's zoom inside and let's delete this. Let's start cutting. It's not very much visible for you because the GoToMeeting will always output out in frames for you, so you'll see a frame-by-frame view only. This is anyway available to us. This entire recording is there on. It's going to be there on the website, so you can see a much more fluidic motion of this particular machine. I've already cut the same part on this machine, so it's very interesting the way it moves, because it's a very different kind of a construction of a machine where the table is completely at an angle into one corner of the machine. So it's nice. It's worth having a look at this machine simulation. Okay, go to stop this, come out, and in the meanwhile, cancel, sorry. You can go into the host CAD and show you the finishing. So you can look at the amount of parameters that I defined for our toolpath definition. It was bare minimum. I had to just pick the blade, just put in the depth of cut, pick the tool, that's it. The toolpath is generated by itself. Okay, now what I'm going to do is I'm going to apply another template, and we are going to cut another blade, the splitter blade we're going to finish, and this is the area that we are going to cut. So I'll apply again from template, finishing of small, use the same. Okay, and if I go to the geometry, we will have geometry out here. Okay, so it's this, yes. So we have the splitter geometry that's selected. Okay, the hub again continues to be face 1. Notice that I have selected the hub not at the place where the splitter is, so it actually doesn't matter where your hub is. It only needs to know what is the shape of the hub, so it just creates another surface of revolution. And of course the shroud, so again I'm using the shroud of the main blade. It doesn't matter because it's the same. Okay, tool in this case is the same. We're using taper ball nose. Okay. Levels, automatic, toolpath parameters, using a maximum distance of 1 millimeter. Again, we are starting at 2% and ending at 95%. It's not complete. We're just leaving the fillet aside. And spiraling from the leading edge again, like what we did for the main blade. Tool axis control, everything again is automatic. I'm going to save this. Oops. The check surface here is empty. Okay. So what we're going to do now is we will define some check surfaces now. Because we are entering into this blade, this area here, this side is very tight. The width is very, very tight. So we will define a couple of these surfaces as our check surfaces. Maybe it's here. Yeah. I'm going to define these two areas here as my check surface. So the software will adjust itself when it's coming close to the surface, including the non-cutting area of the tool. So it will check for these surfaces when it is moving around. You have to use the check surface, like I said before, only when you're in doubt. Here I'm in doubt because of this very tight area when it's trying to cut this. Okay, and we'll keep an offset of 0.5. All right. All right. Let's save this. And let's switch off and run this in parallel. Okay, while this is cutting, we will define the next operation, and that is for finishing the fillets. Okay. So what I'm going to do now is I'll add Multiblade machining. I'm not going to use templates now for a change. We are just going to use the fillet finishing. Okay. In the geometry, I'm going to use fillet finishing, blade splitters and fillets. I'm going to use faces 6 because I'm just going to use show you the fillet finishing on one of the main blades. And of course the hub is this face, again small portion. The tool that we are going to use is the same T1. Okay, levels, automatic. In the toolpath parameters, I'm going to use in the technology where number of cuts, I'm going to use 5. And side step is 0.5 millimeters. So I'm going to get 5 cuts from the blade side and 5 cuts from the hub side. So it's like an equidistant cutting. And in the sorting, I'm going to use bottom-up cycle. It's going to be starting from the hub side, and it's going to move into the blade. Okay. Everything else is actually going to be automatic. We are not going to see any drastic change in this, in any of the parameters. Okay. So I'm going to save this and calculate again this in parallel. Now the fillet finishing is generally a slightly lengthier when it comes to calculation. So that's the reason I put it in parallel. And then I have the results of the small blade. You can see that when it created this particular side of the toolpath, it actually took care of these two surfaces to avoid the surface to be gouged. So it's essential that when you go into areas that are very tight for the tool, you have to define the elements for gouge check. All right, so I'm going to switch off that. Okay, the fillet's also ready. It's nicely done. So you can see that it's covering the entire area. So if I run this simulation, before that let me put on the settings and switch off the machine simulation, any verification of the simulation. I just want the part simulation to run. Okay, let me open the door again and show the part. Let's hide that and the toolpath. So you can see the toolpath as well as the part. Okay, can switch off the toolpath and run this pretty slowly. It's going to be a bit staggered on your screens because GoToMeeting, like I said, doesn't support fluidic motion in terms of simulation on machine simulation. But anyway, for people who would like to see this machine simulation in a much smoother way, can go to our website probably by tomorrow morning or on Friday. This particular video will be up, and you can see it much more smoother on that video. All right, let me stop this. And what I'm going to do now is I'm going to apply the hub finishing. Okay, so I'll add hub finishing, Multiblade. Okay, Multiblade hub finishing, and we will use complete set of blades. So what I'm going to do is I'm going to finish the part in between these three blades, the two main blades and one splitter. Of course, the hub is phase one. The tool here is same tool, taper ball nose. Okay, the technology. Going to use a maximum distance of 1 millimeter or even less. Let's go 0.5. Sorting. That's going to be zigzag starting from the leading edge. Okay, this is automatic. Tool access control. Again, like I said, there is nothing much to choose from. Most of the parameters, they work almost 99% of the time. Link, it's automatic. Gouge check, not needed. We're not going to rotate the toolpath, so we're going to have a single tool. So we save it, and we can put this and calculate a regular calculation. This would take about a minute or so. So what we have seen till now is we just took apart. We had a stock from turning. It was a turn stock. We took it in Solid Verify, saved that turn stock as an STL geometry. That STL file we brought into this particular part, superimposed on it. It's automatically done once we define the stock. And then we defined the roughing. We defined finishing of the blade. We've defined finishing of the small blade, machined the fillets separately, and now we are cutting the hub. That toolpath also has been calculated. The whole gist or the whole takeaway from this particular webinar that you've seen till now is that machining an impeller couldn't have got much more easier than this. It's very, very easy. I mean, imagine if the same impeller was to be machined using a regular 5-axis engine where you had to define everything by yourself. Getting a result as good as this is actually a major, major work. And you know honestly that most of the times you can never get it as good as the result that you have seen today inside the Multiblade application. All right, so this is my hub finishing. Okay. Maybe what we can do is we can edit this and change a couple of parameters here. Instead of 0.5, I'll make 1. Okay, sorting. I think from the leading edge is fine. You can go left to right. Save. Run this in parallel. Because I just want to open up the roughing again because we used a slightly different technique there. Like we are going left to right in hub finishing, but if you look at the impeller, and if you look at the wireframe simulation or the host CAD simulation, we have slightly done it differently. We have we're going from the center. You can see that we're going from the center and we are going away. So it's different way of cutting during roughing. We have taken the center path and then we have expanded it towards the blade. So we enter from the center and then expand our way out to the blades. A nice way of doing it. You can see that. We're going from the center and we're going out. All these connections, by the way, are automatically done by SolidCAM. The external connections which you're seeing in green are basically connected automatically by SolidCAM. They save a lot of air movements, and when it's moving from this point to this point, it's already taking the depth of cut. So it's done very nicely, and you can see these movements very nicely on the machine. There are no jumps on the machine as such. All right, so if I simulate this, switch off the tool, show you this, you can see that the hub has been nicely finished, touched up very nicely. Okay, so the takeaway from this particular part that we just saw was you can use this part to, you can use the Multiblade application to cut parts like this. Even more complex, even more big parts can be cut using the Multiblade application. I'm going to show you another part which has already been done. This is a part I did last week at one of the technology centers of Mazag. Just get the screen to superimpose here. This was the part. Again, if you look at the diameter, it's not small, it's about 250 millimeter, and the height of this impeller is about 109. So it's not a small part, it's pretty large. We've used the same technique out here. We've used roughing, again going from center to out, and this is the tool path that it generates. Very nice. The yellow are the cutting motions, the green are the links. So we're going from center away, very nicely done. And then we have got the finishing of the blade. Now you can see that this was not done completely because this was an area that was left out. We have got an option to link this area, and this option, when you see the toolpath linking, we did not use automatic. In fact, I switched off the automatic and we used the direct blend because the automatic will take it to the clearance plane. So I over I overrode the application, removed the automatic option, and used the direct blend. Direct blend gives a much nice links. It takes it out nicely, takes the depth of cut, and enters into the other side. And the same thing is applied to our small blade out here and the hub finishing. You can see that it's nicely connecting from one side to the other. Very nicely done. And then the fillets, also the connections used. I overrode the connections and used the direct blend, nicely connected from one pass to the other. Also the same thing for the small blade out here. So if you really look at the application closely, the key takeaways are: one, it's very easy to use. There's not much of a training needed for anyone who wants to cut a multi-blade part on SolidCAM's multi-blade application. Number two, it's very powerful. Any part, virtually any part, can be done using the multi-blade. When I say any part, it's not that you can put any kind of 5-axis. It's only any kind of an impeller. Blisk can be done using the multi-blade application. Any complexity, any size, any kind of a tool. So the package gives you complete freedom to cut the part fast and in a much easier way without spending a lot of time defining the geometries, creating new geometries, creating curves, points, etc. to control the tool. All those things are of the past. It's more of an automatic solution for cutting impellers. Right. I'm done with my presentation today. This particular presentation will also be available on our website in maybe a day or two. So you can have, if somebody wants to relook at this webinar again, they can go to the website and you can actually play it, or you could download it if you have the downloading capability from YouTube. And if there are questions, I'm ready for questions. You can ask me questions, and I'll try my best to answer them in this given short time.
Thank you, Ahmad. Thank you, everyone, for joining us. We'll give you a few more seconds if anyone has any questions, because right now I don't see any questions. Okay, so thank you again, everyone, and thank you, Ahmad, for this presentation, and we will see you all next week. Have a good week.
Thank you.